Previous class we were discussing on porphyrin rings, and we have also given quick introductions about of heme proteins and non-heme proteins. So heme proteins are if PR rings plus AP atoms are there, and non-heme proteins means that PR rings which not present, only AP atoms is there. Okay, so let's discuss more details about of heme proteins and non-heme proteins. Okay, so first is heme protein. Heme protein. So heme protein means PR ring is there, that is porphyrin ring. This is called PR shortcut. Okay, plus AP atom is there. Okay, this is called heme proteins, and this heme proteins it is mainly found in animals, and human beings efficiently can get that heme proteins from this, if this is heme protein. So you can say that human beings easily observe Fe from heme proteins. Okay, so this is about of the heme proteins, and whenever we say about of this non-heme proteins, I take another pen. Non-heme proteins, what is that porphyrin rings, here plus here, that non-heme proteins, that there will be no porphyrin ring, means that porphyrin ring is not present for non-porphyrin ring, non-heme proteins. Okay, only Fe is present. So it is found in both animals and plants. Okay, so this non-heme protein means there will be no porphyrin rings, that porphyrin ring is not there. So we have discussed porphyrin rings detail in previous class. Okay, so that porphyrin ring is not present for case of non-heme proteins, and it is found in both animals and plants. Okay, and human beings are not easily that observes these porphyrin rings. So for him you can say that human beings not easily or not efficiently observe protein from non-heme proteins. Okay, so these are the details about of heme proteins and non-heme proteins. So we will discuss one by one heme proteins and non-heme proteins. So first we will talk with non-heme proteins. Okay, so let's start with non-heme proteins. Start with non-heme proteins. Okay, so non-heme protein means we say that no porphyrin ring, that is called PR plus Fe atoms. So here only Fe atoms is there, but that porphyrin ring is not there. So here basically what we say that here that Fe is there plus sulfur atoms is there. Okay, sulfur atoms. So if I discuss about of this non-heme proteins, then the types will be, so what here the no porphyrin rings. So here what is there, that irons and sulfur. So you can say iron, sulfur protein. So here iron and sulfur are there, and what we see that this here the sulfur, okay, this sulfur can be two types we can get. One is, let's say, the labile sulfur, another is non-labile sulfur. Okay, so in labile sulfurs, what is it? This is the inorganic sulfur. Okay, this is inorganic sulfur. Okay, and this non-labile sulfur, this is organic sulfur. Okay, and this inorganic sulfur, it can be replaceable, it can be replaceable, and it is non-replaceable. Okay, so replaceable and non-replaceable means, let's say here this is M, these are the sulfurs. Let's say if I add any HCl, excess is given, then what MHH will get, okay, MHH. But here, if that M as sulfur are there, if I am adding that HCl, then no reactions will happen. Means here that sulfur will get replaced by hydrogens if it is inorganic sulfur, if it is the labile sulfurs. For case of non-labile sulfurs, then it will be non-replaceable if you add any HCl. Okay, excess also if you give, there will be no reactions. So there are the two type of sulfurs we will get. One is labile sulfur, another is non-labile sulfurs. Labile sulfurs are inorganic sulfurs and non-labile sulfurs are organic sulfurs. Okay, so our types is sulfurs, iron sulfur proteins. Okay, so these are the just for understanding. So our is iron sulfur proteins. So we are discussing on iron sulfur proteins. Okay, so in this iron sulfur proteins, what we see here, that here we get one Fe atoms and another we get, that is sulfur, and sulfur can be labile or can be non-labile. Okay, this is the first points. And about of iron sulfur proteins, what we see that wherever this Fe atoms is there, Fe atoms is always tetrahedrally it is always tetrahedral structure with 4 sulfur atoms. So Fe atom is always tetrahedral structure with 4 sulfur atoms, and this sulfur can be labile and non-labile, and sulfur can be labile and non-labiles. Okay, and what you see here, and we see that this Fe can be so +3 oxidation also you can see, +3 or +2 oxidation state. So this Fe atoms, you will see that in non-heme proteins, this Fe either it is present in +3 oxidation state or +2 oxidation states, and wherever this Fe is present, in every case this Fe is always tetrahedral, it always attached with 4 sulfur atoms, and that is in a tetrahedral structure. Okay, this is very important points. Means Fe atoms wherever it is present, it always making bond with 4 sulfur atoms, and they are in a tetrahedral structure. Okay, and Fe can be in +3 or +2 oxidation states, and Fe can be 1 to 8 number of that I can say. Fe can be, sorry, Fe can be present either 8 or either 1 to 8 number of, okay, that I can write. So Fe can be 1 to 8 number, or I can write, sorry, number of Fe atoms can be 1 to 8, and the general formula of iron sulfur atom is FeNSN, where Sn is, where N, here this Sn is represents labile sulfurs. Okay, so wherever this Sn is present, then we will say that for this general formula, if FeSn is there, then this Sn stands for labile sulfur, not non-labile sulfur. This always stands for labile sulfur. Labile sulfur means inorganic sulfurs, means that is replaceable sulfurs. Okay, so this is the general formula of iron sulfur atoms, sorry, iron sulfur proteins, that is FeNSN, and this Sn stands for labile sulfurs. Okay, so now we will discuss on classifications of iron sulfurs. So I will discuss classifications of iron sulfur. Okay, so on the basis of number of labile sulfur and number of Fe atoms in iron sulfur proteins, can be two types. Okay, and one is that we will discuss. One is rubroductions, another is paradoxins. Okay, so this rubroductions and paradoxins, first we will discuss about rubroductions, then we will go for paradoxins. So these are the types of iron sulfur proteins. So iron sulfur proteins on the basis of number of labile sulfurs and number of Fe atoms can be two types, rubroductions and paradoxins. Okay, so now first we will discuss about rubroductions. So I says that general formula of a iron sulfur protein is FeNSN. This is the general formula. I can write general formula of iron sulfur protein is FeNSN. So here for rubroductions, what it is, N is equal to 1, sorry, Fen, that is Fe here is 1 and S equal to 0. This is for rubroductions. I can say for rubroductions Fe are 1 and S is 0. It means that here one Fe atoms is present, Fe atom is present, and one level sulfur. Whenever this SN means level sulfur. Okay, so one, sorry, this is 0, right? So 0 level sulfur is present. It means that no level sulfur is present, and we have discussed that whenever Fe is present, it always attached with 4 sulfurs. It may be level or it may be non-level. But means if Fe is present, means it must have that 4 sulfur atoms. That may be level or that may be non-level. But here that level sulfur is 0. It means that 4 non-level sulfur is present. Okay. So if is Fe, then Fe condition is wherever Fe is present, it always present in a tetrahedral structure with 4 sulfurs. That sulfur can be level or non-level. So since here level is 0, means other 4 sulfur must be non-level sulfur. So here sulfur is present, but that are the non-level sulfurs. Okay, this is the sulfurs and tetrahedral structures, and this is CH2, this is cysteine. Okay, this is CH2, this is cysteine, this is CH2, this is cysteine. Okay, this is CH2, cysteine. Okay, this type of structures you will get. Okay, so these are the non-level sulfur. Okay, so what we found here for this reproductions, what we found that one Fe atom is present, okay, and 0 level sulfurs and 4 non-level sulfurs is present, 4 non-level sulfur. Okay, so wherever Fe is present means it must be in a tetrahedral. Fe present means it is must be in a tetrahedral structure with 4 sulfur atoms. Okay, so here the non-level sulfurs are 0, means 4 non-level sulfurs are there. Okay, also here this cysteines, which this cysteine is electron rich. So here the color of this compound is due to LMCT, because this cysteines, this is the ligands. So from this ligands electron is going to metals, so this is color due to LMCT. Okay, and it is also exist in 2 forms. One is it is available in 2 forms. One is oxidized, another is reduced form. So only one sulfurs, whenever it present in oxidized form, this is present in +3, and whenever it is present in +3 oxidation state, and whenever it is present in reduced form, it is present in +2 oxidation state. Okay, so these are the about of this level sulfurs, and this structure is something like this, and it is tetrahedral structures, tetrahedral. Okay, now we will go to next types, that is paradoxins. So reproductions, where the general formula is this, and here that this is this. Okay, so next type is paradoxins. So we know that the general formula of paradoxins is general formula of iron sulfur protein is iron sulfur protein is FeSN. So here that paradoxins, it is available in 3 forms. Here it is available, I can say paradoxins is available in 3 forms. One is in Fe2S2, another is Fe4S4, another is Fe3S4. Okay, so these 3 forms it is available. Okay, so now first form is Fe2S2 form, where cogeneration structure, that is FeNSN, and this says that level sulfur. Okay, so from here what I understand, that 2 Fe atoms is there, 2 Fe atoms present, and 2 level sulfur is present, and also what you know, that whenever that Fe is present, it always available in a tetrahedral structure with 4 sulfur atoms. Okay, so one Fe atoms always available in tetrahedral with sulfurs. This is the conditions for non-heme proteins. So here 2 Fe atoms are there. So how the structures will look like? So make sure that Fe is always connected with 4 sulfur atoms. So how it is possible? Let's say here one Fe, here one Fe. Okay, so what you do here we will do one level sulfurs. Okay, here another level sulfur. Okay, so and then you will do here again another sulfurs, because one Fe always 4 sulfur atoms it is connected. So here also I can do one sulfur. So Fe has connected to 4 sulfur atoms. Okay, 4 sulfur, 1 2 3 4. Here also 4 sulfur atoms. Okay, so what we found here, that 2 Fe atoms present. From this formula you understand that 2 level sulfurs. Yes, 2 level sulfurs is drawn. These are the 2 level sulfurs, and 4 non-level sulfurs are also present. Okay, so 1 2 3 4, 4 non-level sulfurs present. Okay, so this is the form of Fe2S2. Okay, and this Fe2S2 it is called as plant protein, or we can say photosynthetic paradoxins, or photosynthetic proteins, or photosynthetic plant proteins. Okay, so this is also photosynthesis paradoxins proteins that we call. So this is mainly used in photosynthetic plants. Okay, that's why we call as plant proteins or photosynthetic plant proteins. So it is also available in 2 forms. It is available in 2 forms. One is oxidized, another is reduced form. So in oxidized form, so 2 Fe atoms are there. Yes, 2 Fe atoms, and Fe atoms present either close to M +3. Okay, so here that both Fe atoms are exist in +3 oxidation atoms for oxidized form. Okay, in oxidized, both Fe atoms in +3 oxidation state, and for reduced form, one Fe atom in +3 oxidation states and one Fe atoms in +2 oxidation state. So you remember that Fe is present. First condition is it is present tetrahedrally. It means it is attached with 4 sulfur atoms, and Fe is always present either +2 or +3 oxidation state in whole non-heme proteins. Okay, these are the general things. Okay, so it cannot exist as +4 or +5. It exists as a +2 or +3, and wherever Fe is present, it is attached with 4 sulfur atoms. That are the two conditions for non-heme proteins. Okay, so it is available in, so for oxidase, if both Fe means 2 Fe is there, both are in +3 oxidation state. For reduced form, 1 Fe is in +3 oxidation state, 1 Fe in +2 oxidation states. Okay, now we will go that Fe in +3, it means that it is D5, because if it says, so Fe is 4s2 3d6, so Fe3 plus is 3d5. Okay, so both Fe means 2 Fe are there, so Fe3 plus, one is D5, another is also Fe3 plus, that is D5. Okay, so here that D5 means I will draw 1 2 3 5. Okay, here 1 2 3 4 5. So whenever I will do that paramagnetic coupling, if you do that paramagnetic coupling, that we will study detail about of this paramagnetic coupling in higher inorganic spectroscopy. That if you do that, then what you will do, that everybody will be pair. Okay, 1 2 3 4, here also 1 2 3 4 5, so 1 2. Okay, so all are pair, means that here that unpair electron is 0, unpair electrons is 0, so total spin is 0. So if total spin is 0, if no unpaired electron is there, then it is ESR inactive. So for ESR active, that number of unpaired electron must be present. Okay, because for ESR active, number of unpaired electrons must be present. So here number of unpaired electron is 0, so ESR inactive. Okay, so let's next discuss for that reduced form of this Fe2H2 paradoxins. What we say that one Fe is in +3 oxidation states. So +3 oxidation state means Fe3 plus, that is D5, and other is +2, that is Fe +2 means that is D6. So here we will draw the structures 1 2 3 4 5, and this is 6. So 1 2 3 4 5, another is 6. Okay, so if you do that paramagnetic coupling, if I do that paramagnetic coupling, then what will say, what will do, 1 2 this is there, this 4 and this 4 will be coupled. That means that this will be there already. Okay, and this 4 will couple to, and this will be remained, or I can do in other pen so that you can understand it. So this is already coupled. Okay, so then let's say this is in, I will do in other pen. Okay, so this 4 will this 4 and this 4 will couple, so 1 and this has remain, so this will be stay as it is, and this is again already in coupled. So here that unpaired electron is present, so unpaired electron is equal to 1. Okay, and so this is ESR active. Okay, so in reduced form, Fe2H2 is ESR active. Okay, okay, so this is ESR active. Okay, now next type is, so it is present paradoxin is 3 forms. We say first is Fe2H2 that we have discussed, another is Fe4S4. Okay, now we will discuss second case, that is Fe for S4. So it is actually most stable and most common paradoxins proteins, and it is found in active site of nitrogen fixation bacteria. Okay, and what you say that its structure is that general formula of iron sulfur protein is Fe and Sn, where Sn represent that number of level sulfur. So here level sulfurs are here Sn equal to S4, means that level sulfurs are 4. Okay, so also we know that wherever Fe is present, it is always attached with 4 sulfur atoms in the tetrahedral structures, and Fe is present in +3 or +2 oxidation state in full non-heme proteins. So how the structure will look like? So one Fe always attached with 4 sulfurs. Okay, that you have to remember wherever you are doing that non-heme proteins. Okay, how the structure will look like. Let's say if I do the structures, so this is somehow the cubic structure. So this Fe4, it is cube-like structure that we call as Cuban structure. How it will look? Let's say Fe is there and S, and not that Fe, no bond is there, no bond should present, and S no bond should present. Okay, while doing the structure, this you have to remember. So here, let's say if I do S, Fe, let's say S. So now if I do that Fe here do that S, I do Fe, here do S, then that I will join here this. Okay, so here we see that not that this Fe is always present in, it will always attach with 4 sulfur. Okay, so here it is already attached with 1 sulfur and 1 sulfur, and not that this should not be, there should not be FAP bonds and there should not be SS bond. So no SS bond is there, then this our structure is good, our structure is right. Okay, so here already attached with 4 level sulfurs. So non-level sulfurs will generally in the formula you will not write. Okay, but if there is no level sulfurs, then there should be non-level sulfurs. So here it already attached with 4 level sulfurs. Okay, so this hydrogen always attached with 4 level sulfurs, 4 sulfurs. It may be non-level, it may be level. So it already attached with 3 level sulfurs. So one is remain. So that will be attached with non-level sulfurs. That is S. I can say CH2 16. Okay. Similarly, here if you see this bonds. Okay, here 1 sulfur is here, 1 sulfur is here, 3 sulfur attached, and Fe always attached with 4 sulfur atoms. So one more you have to draw. So here also you will draw here S CH2 16. Okay, this is the non-level sulfurs. Similarly here, okay, one is here, one is here, one is here, so another is remain. So another we will draw here S CH2 16. Okay, similarly here, this is 1, this is 2, 3, so 1 has remain. Here also one H remains, so again we will attach one S CH2 16. Okay, so this is the structure of the Ap4 SO4 structure. So what we see here, so always remember that wherever Ap is present, it always connected with 4 sulfur atoms. That sulfur may be label, may be non-label. Okay, so we will now write some points. What are they here? That how many Ap are there? 4 Ap atoms are present. 4 Ap atoms are present. How many level sulfurs? 1, 2, 3, 4. Okay, so 4 level sulfurs. 4 level sulfurs. How many non-level sulfurs are there? 1, 2, 3, 4. So again 4 non-level sulfurs. Sulfurs present. Okay. So one thing, note that I have drawn this picture, that's why I get this structure. If I do this structure in a different manner, let's say if I draw this structure, instead of Ap I will draw here S, and here I will go for Ap. Here I will do, here instead of Ap I will do S, and or I will do any, instead of F if I draw S, and here if I do Fe, and if I do Fe, and note that no APP, no SS bond should not be present. Okay, so here I will do S, here I will do Fe, here I will do S, I will do Fe. Then I will not get this type of structures if I instead of P if I put S. Why? Because you see here SFE is fine, FPS is fine, FPS is fine, PS is fine. Okay, so this is also fine. So what are the things are there? 4 non-label sulfurs are present, and 4 label sulfurs and 4 Ap atoms are present. And anything else? Okay, these are the about of this Ap4 atoms, and it also exists in 2 forms. Ap4 exist in 2 forms. Okay, one is oxidized, another is reduced form. So in oxidized forms, Ap4 it is what so whenever Ap is present, it is present either +2 or +3 oxidation states. So here the 2 Fe in +3 oxidation states and 2 Fe in +2 oxidation states. So +3 or +2, only this 2 oxidation state only present, not +4, not +5. Okay, so for oxidized 2 Ap in +3 oxidation state and 2 Ap in +2 oxidation states. For case of reduced forms, that 3 Fe total is 4, so 3 Fe is in +2 oxidation states and 1 Fe in +3 oxidation states. Okay, so if I do this electron count, so 2 Fe in +3 oxidation states means Fe +3, and this is D5, and Fe 3 plus, this is again D5. Then you see that 1 2 3 4 5, 1 2 3 4 5. So if you paramagnetic coupling, then all will be coupled. Okay, and another Fe in +2 oxidation state, on that also Fe 2 plus, that is D6, and then Fe 2 plus, that is D6. So here 1 2, okay, 1 2 3 4 5 6, here also 1 2 3 4, 1 2 3 4 5 6. So here if you decoupled paramagnetic coupling, if you do, then you will get like this. This are already coupled, this 2, and this 4 again coupled. Okay, 1 2. So all are pairing, means no paramagnetic, means no unpaired electron. So this is ESR inactive. Okay, and for case of this reduced form, so 3 Fe in plus 2 oxidation state. So let's say Fe2 plus, that is D6, another Fe2 plus, that is again D6, another Fe2 plus, that is again D6. Okay, and another is plus 3 oxidation states. So another is Fe3 plus, that is D5. So here 1 2 1 2 3 4 1 2 3 4 5 6. Here also let's say 1 2 3 4. Okay, and this is again it says, let's say 1 2, let's say 1 2 3 4. Okay, and this is D5. So let's say 1 2 3 4 5. So here if you decouple this, then this will be coupled 1 2 3 4 1 2 3 4. Okay, so 1 2. Okay, this, and now if you do this and this coupling, paramagnetic coupling, this and this, then what we find here, so this and this is already coupled. Okay, and this is 5 and this is 4. So this 4 will couple and 1 will remain unpaired. Okay, so this is 1 2 and 1 will be, sorry, 1 will remain uncoupled. So here, so 1 is remain unpaired. 1 unpaired electrons you will get. So I can write, so 1 unpaired electrons. So this is ESR active. Okay, so this is the structures of Epi4 S4 types. Now next we will discuss the third types. Third type is Epi3 S4. Okay, third type is Epi3 S4 types. So it is present in, sorry, Fe3S4. It is one type of paradoxins, and what you see here, so it is the, we can say Fe4S4. Let's talk about its structure directly. So here what, from here what you understand, that it has 3 Fe atoms and it has 4 Libel sulfurs. Whenever you say that, this always represent the Libel sulfurs. Okay, 4 Libel sulfurs. So its structure is somehow looks like this. Let's say here S Fe S. Okay, and now here I will do Fe, here S, or here I will write Fe, here is Fe. Okay, so this bond. So wherever this Fe is present, this is always attached with 4 sulfur atoms. So here we see that this Fe is attached with 4 sulfur atoms, these sulfurs and these sulfurs, 2 only. Okay, so another you need to draw. So it will go here S, Okay, so how many sulfurs? 1 2 3, 3 sulfurs. So it has to be always 4 sulfurs. Okay, that we'll discuss later. Let's say for this is also 1 2, and this is 3, and for this 1 2. Okay, for this 1 2, and for this 1 2. So its structure is uh, I think its structure is somehow, okay. So what I do here, okay, so this sulfur again will join here. Then how many? For this 1 2, sorry, this is for this 1 and 2 and 3. Okay, and for this 1 2. So for this Fe, so only 3 Fe, so we will not draw here. So only 3 Fe atoms are there, right? Okay, so how many total sulfurs? So here total Fe atoms are 3. So 3 Fe atoms, 1 2 3, and total sulfur atoms are 4, 1 2 3 4. Okay, so this is the structure. So you see that this Fe is attached with 1 2 3. This will also I will do 1 2 3. So always Fe is present attached with 4 sulfur atoms. So one more sulfurs you have to draw, that is non-labile sulfurs. So I will do here as CH2 cysteines, or here also another sorry Fe is attached with 4 sulfur atoms. So here I will do this because this is 1 2 3, but Fe always attached with 4 sulfurs. I will do as CH2 cysteines. Similarly here this is also another S CH2 cysteines. Okay, similarly this and this is also another S CH2 cysteines. Okay, so you see that every case this where this iron is attached with 4 sulfurs, 1 2 3 4. This also 1 2 1 2 3 4. This also 1 2 3 4. Okay, so this is the structures of Fe3S4. Okay, so it has 4 labile sulfurs and how many non-labile sulfurs? 1 2 3. Okay, so 3 non-labile sulfurs. So it is also exist in 2 forms. It is also exist in 2 forms. One is oxidized, another is reduced. Okay, so oxidized forms, what are there here? That 3 Fe, so all 3 Fe are in +3 oxidation state, in oxidized form. Okay, and for reduced forms, what is said that 2 Fe are in +3 oxidation state and 1 Fe in +2 oxidation state. Okay, so now we will discuss that whether the AS are active or not. So 3 Fe are in +3 oxidation state, so Fe 3 plus means that is D5. So another Fe3, so this is again D5, another this is again this is D5. So if I just a minute. Okay, so this all are in +3 oxidation states. So this Ap3D5 means, let's say 1 2 4 5, let's say this is 1 2 3 5, let's say this is 2 3 4 5. So if you, this is parametric coupling, then you will get like this structure, but this will be remain at is unpaired. So this is equal to pi by 2. So overall spin is pi by 2. So here that unpaired electron is present, so this is ESR active. Again, in this case 2 Ap are in +3 oxidation states, so Ap3 plus, that means D5, and Ap3 plus, that means this is also D5, and 1 Ap is in +2 oxidation state, that is D6. So these are, let's say 1 2 4 5, and this is 1 2, let's say 1 2 3 4 5. So if you paramagnetic coupling, then this will be paired, but this will remain as unpaired electrons. For coupling this, no any unpaired, no any this D6 are not present. So here that total spin is, that is 6. So this is 5 6. Okay, so the total spin is 4 upon 2. Okay, so here unpaired electron present, so this is also ESR active. So what I found is here that here both oxidized and reduced form as ESR active. ESR active, this also ESR active. It means that for Ap3S pores, both oxidized and reduced forms are ESR actives. For this case of, this is the case of Ap3S pore. Okay, so whenever you go for Ap4S pore, oxidized and reduced form, for Ap4S pore, what we see here that for oxidized this is ESR inactive, for reduced that is ESR active, means one is inactive, one is active. Okay, for Ap4S pore, and whenever you go for Ap, this is Ap4S pore, and whenever you go for this is Ap2S2, Ap2S2 for oxidized form, this is ESR inactives and this is ESR active. Okay, that is for Ap2S2, Ap2S2. So what we see here that for paradoxins, for all the cases, what we see that only Fe3S4 case, both oxidized and reduced form, these are ESR actives. Okay, so if I give sum of, so for Ap2S2, what it says that oxidized and reduced, and this is what is said, this is ESR inactive, and this is ESR active. And for Fe4S4, this is also oxidized form and reduced form, and this is ESR inactive, and this is ESR active. And another is Fe3S4, this is also oxidized and this is also reduced, and this is ESR inactive, this is also ESR inactive. Okay, that's what you see that for Fe2S2, here one is inactive, one is active. For Fe4S4, one is inactive, another is active, but for Fe4S4 both are ESR active. Okay, here this is inactive, this is active, here this is active, this is inactive, but here both are active. Okay, so we see that here ESR active, this is ESR active, and for here this is inactive, this is active, here also you see that this is inactive and this is active. Okay, So what you see that generally for oxidized case all are inactive, every case, but here for oxidized also this is active. This is active. This is also active. Okay, so for AP3S4 for oxidized reduced form also active, but for AP4S4 for oxidized this is inactive, here also for oxidized inactive, but here for oxidized or reduced both case it is active. Okay, so this is about of that non-heme proteins. So we have discussed here that paradoxins, another is reproductions. For reproductions we see that its structures and detail about of reproductions we have discussed, and we have also discussed about of the paradoxins. So now next we will move to the next, that is heme proteins. Okay, next topic is, next we will move to the heme proteins. So we see that heme protein means here porphyrin ring is present. Okay, so here porphyrin, here porphyrin ring, that we can say PR is present plus AP atom is there. Whereas for non-heme proteins, what we see that non-heme proteins, what we see that no porphyrin ring plus AP atoms. Okay, but here the porphyrin ring is present. Okay, and it is found mainly in animals. Okay, so I am rearranging it. So it is found mainly in animals, and human beings efficiently observe, means efficiently able to take, able to okay. So human beings efficiently able to take these proteins. Okay, so in heme proteins we will and it is found, and it is found in, so we will get this heme proteins, or we can get this type of heme proteins in, let's say, cytochromes, or this hemoglobins and this myoglobins and this chlorophylls. Here we get this heme proteins. Okay, so before discuss on it, it is important to draw the structure. So structure is that porphyrin ring. So because here that porphyrin ring is present, yes, this porphyrin ring. So in past class we have discussed about of this porphyrin rings. So we will draw the porphyrin ring structures again. So let's say this is N, this is N, this is N, this is N. Okay, sorry, this is okay. Okay, so now we will draw what we have already drawn in this previous class. So here I will do attached, okay, and here I have already saw how to draw the structures. So now I am drawing by quickly I am drawing because I already says how to draw this structure. Okay, so now I will start from here. One, this, then remain this, remain this, this, and this remains. This will comes to here. This remains, and this goes to here. This remains, comes to here. Then this remains, so goes to here. This remains, goes to here. This remains. This goes to here. This goes to here. Okay. So this is 11 pi bonds are there, and see this is that no lone pair is there. So this lone pairs, and here also the lone pair is there because adjacent nitrogen atoms no pi bonds are there, so lone pair is there. So this will be Fe atoms if you draw, so this will be coordinately bond. Okay, and this is simply the this bond. So this is the porphyrin ring, okay, with Fe atoms. Okay, Fe atoms is there with bond with 4 nitrogen atoms. Okay, so in case of non-heme proteins, on that case Fe is attached with 4 sulfur atoms. Okay, but this is about of the heme proteins. Here nitrogen atoms are there. Okay. So now what you look here, that here this Fe atoms here, what it says that, okay, and here so this structures is somehow like this. Okay, and this here, what is lies here, here if I draw here CH3, so here if I draw that R1, this structure is somehow looks like this. Let me look. CH3, here this R1, and this structures is again here also CH3, here is R2, and here it will be CH3, and here it will be CH2, CO minus, and this structure is again here CH3, and here again that CH3, CH2, CO minus. Okay, so this is the structure of porphyrin rings with Fe atoms. And what is says that if R1 equal to R2, and if R1 equal to R2, and that is equal to CH2 double bond CH2, then it is found, Okay, if this, then it is found in cytochrome B, and that cytochrome B, or this is hemoglobin and myoglobins, there it will found. Okay, and next case, if R1 equal to R2, and that is R1 equal to R2, and that is equal to CH3 here S, and this is protein, then it is found in, then it is found. Okay, so it is found in, that is cytochrome C. Yes, that is found in cytochrome C. And another third case, if R1 is equal to CH2 CH2 and R2 is equal to that is C18H30OH, then it is found in cytochrome A. Okay, so these three things you have to remember, and that is what, that here I put this R1 and R2. Okay, this R1 and R2. Okay, according to this R1 and R2, that value will change. If this R1 and R2, the both case are CH2, then this is cytochrome B. Cytochrome B means that is hemoglobins and myoglobin on that case. And if R1 and R2 both are R1 and R2, here R1 and R2 both are this, then cytochrome B. If R1 and this R2 is equal to CH3 and this is S, then it is found in then it is found in cytochrome C. Okay, if both R1 and R2, if both on R1 and R2 this, then cytochrome B, that is hemoglobins and myoglobins, and this R1 and R2 are both in both are this, then it will found in this. And if R1 is not equal to R2, that is R1 is C2, that is this CH2, and R2 is, that is C18H30OH, then that is found in cytochrome A. Okay, cytochrome A. So what we see here, that cytochrome B, what is say, that R1 equal to R2, that is equal to CH2. Okay, and cytochrome C is, what we say, that R1 equal to R2, and that is equal to C13 and S. Okay, and this is any protein. And if cytochrome is A, then that is R1 is equal to CH2, and R2 is equal to C3, and R2 is C18H30OH. This is called cytochrome A. So both cytochrome B and cytochrome C, R1 equal to R2. Okay, but for cytochrome A, R1 and R2 are different. So why this case? So for that, one thing we have to remember. So whenever that oxygen is flow, that electron, this non-heme proteins, these are we are discussing about of that heme proteins. Okay, so in heme proteins, what you see, that heme proteins, that electrons are flowing from that it binds the oxygens. Okay, so what you say, that first cytochrome B, then cytochrome C, then cytochrome A, then it binds to O2. Okay, so you see that this cytochrome A binds to oxygen atoms. Okay, since it is binding oxygen atoms, that's why this is a different, like R1 not equal to R2, but the cytochrome B and cytochrome C are both R1 equal to R2. Here also R1 equal to R2. Okay. And if we discuss about of the reduction potential, then what we see that this cytochrome B is lowest, then cytochrome C will come, then I think then cytochrome A, and this value is 0.03 volt, and this is 0. Sorry, this is 0. This is 0.26 and this is 0.4 volt. Okay, this is the reduction potentials. And the order of the electron flow systems in respiratory chain from food is this. Okay, this is the electron flow from respiratory chain, electron flow to respiratory chain, from food. Okay, so that is cyto B, cyto C, cyto A, then O2. Okay, so this you see that here this cyto C is totally that whole are it is coordinate, one side cytochrome B, one side cytochrome C. So if I discuss you will not discuss about cytochrome B because this is found in hemoglobin and myoglobins. Whenever discussing on that, we will discuss on cytochrome B. So now we will discuss about of cytochrome C and cytochrome A. Okay, so if I discuss about of that cytochrome A, or first we will discuss about of cytochrome C, then what you see that it is totally, you see that in the electron flow to respiratory chain from food, you see that it lies in the middle. It means that what you see here, it is coordinately unsaturated. It means that whenever cytochrome C structure, what you see here that first this AP is coordinately bonded with 4 AP atoms. With that, one atoms is with that is N atoms of histidines, and another is S atoms of methionines. Okay, S atoms of methionines. So this cytochrome, it is coordinately unsaturated, and what we say that its four coordinates are occupied by N atoms of porphyrin rings, and fifth coordinate is N atom of histidines, and sixth coordinate is S atoms of methanes. Okay, so this is coordinately unsaturated. It means that what I say this so cytochrome C can't bind with or cannot react, can't react with O2 and poisons, and or we can say can't react with coordinately, but indirectly but indirectly by electron transfer method. Okay, so it is inert to both O2 and O2 as well as poisons as well, and O2 as well as poison like CO and Cn minus. Okay, because it is coordinately because it has no coordinate site. Okay, because it has no coordinate site. So this is about of that cytochrome C. Okay, now next we will discuss about of that cytochrome A. So what we find that it is last what you see here, it is the last link in respiratory chain, and it binds to O2 and reduced, and it each bind with O2. Okay, and what you see that it is 5 coordinate in absence of, or it is 5 coordinate before binding to O2. Okay, so before binding O2 it is 5 coordinates. Okay, and here also we will discuss about of this cyanide poisoning. So another important concept is cyanide poisoning. So what is the cyanide poisoning? So this cytochrome A binds with O2. Okay, so whenever this cytochrome A binds that CO and Cn minus instead of O2, then that is called cyanide poisoning. So whenever the cytochrome A binds with Cn minus or CO instead of O2, then it called cyanide poisoning. Okay, so what we see here that this cytochrome A will binds with oxygens. Okay, so today after this, in previous class we will discuss more. Thank you.